Hi everyone, welcome to my presentation, and today we are going to talk about one of the fundamental branches of business statistics. Today we are going to bring data, event, time and a model together and talk about one of my favorite topic in statistics called survival analysis, understanding the time to event data. I'm Kiran Vatra, and today we are going to dive into the world of survival analysis with a focus on understanding the time to event data. By the end of this presentation, we should have a clear idea on what survival analysis is all about, why it matters, especially in the field of actuarial science, healthcare, and business, and how it can help us make informed decisions. Introduction to Survival Analysis. Survival analysis is an essential branch of statistics that is all about understanding the time to event data. Whether it's predicting the lifespan of a product, or forecasting the patient survival rate in healthcare, or estimating the risk of insurance claim in actuarial science, survival analysis plays a crucial role. Some of the key concepts we need to understand as we dive into the time to event data analysis are the survival function, the hazard rate, and censoring. To understand survival function, we need to know two things: event and failure time. An event can be any instance that we are interested in, and failure time is the time starting from a point till the given event occurs. For example, the time until an insurer makes his first claim, or the time until next earthquake strikes, the time until a company fails, the time until a stock hits its striking price, or the time until a cancer patient dies. Now, if we let t represent this failure time, the probability that a patient or a device or any object of interest will survive past a certain time is called survival function. And it is written as st equals to probability of t greater than t. Statistically speaking, the cumulative distribution function ft shows the probability that the cancer patient will die within time t, which is written as ft equals to probability of t less than equals to t. Hence, the survival function st, which is the complement of ft, shows that the probability that the patient will survive past this point. Now let's have a look at a quick example here. Let's say from the point of us being diagnosed with cancer, the probability that the person dies in exactly 2 years is 0.3, and the probability that they die in exactly 4 years is 0.25, and so on. Now the probability that they die within the first 2 years after being diagnosed with cancer, which is represented by the CDF, is 0.3, and the probability that they will not die and live more than 2 years is given by the survival function, which is 1 minus zero point 0.3 equals 0.7. Similarly, the probability that they die within the first 4 years, which is 0.3 plus 0.25, which is given by 0.55. So that's the probability that they die within the first 4 years, and the survival function represents that the probability that they live beyond 4 years, which is 0.45. Now let's show this in graph. And as we expect, the probability of survival decreases as the time t increases, indicating a lower likelihood that a cancer patient will make it past 9 years after first being diagnosed with cancer. Now let's have a look at another concept of survival analysis called hazard rate. Unlike the survival function, which shows the probability of survival, the hazard rate gives us the probability of instantaneous risk at any given time. In the case of our cancer patient, it is the probability that the patient will die in exactly t plus h years, given that they have survived up to time t, as shown in the diagram here. To put this in statistical term, hazard rate is represented by lambda t, which shows the limit of t less than equals to t plus h, given that t is greater than t as h gets smaller, which is equal to the probability of event occurring between t and t plus h, given that the person has survived more than 2 years. As we take a small value of h in discrete case, we can say that the person dying in between t and t plus h is equal to the person dying at exactly time t, which is hence equal to ft over st. Now let's see this with the same data we had before. From the previous data, we have seen that the probability that a cancer patient will survive for more than 2 years is 0.7, and the probability that they survive for more than 4 years is 0.45. So using the hazard rate formula we have discovered, we can calculate the probability that the person dying in exactly 2 years is given by 0.3 over 0.7, which is 0.429, and the probability that they die in exactly 4 years, given that they have survived up to 4 years, is 0.556, and so on. So plotting this in graph, we can see that the hazard rate shows the likelihood of instantaneous death at any given time. It doesn't necessarily follow a trend from our data. We know that no one has lived past 9 years, which is shown in the hazard rate curve as it spikes up towards the end. Now we're going to look at the final concept we're going to discuss in survival analysis called censoring. In statistics, censoring is a condition in which the value of a measurement or observation is only partially known. But what does this actually mean? Let's take an example. Let's say we conducted a study to measure the impact of a drug on mortality rate on 100 patients. The event we are interested here is death. Every time one of the patient dies, we record their time of the death. For example, let's say 25 people died in 1 year, 20 died in 2 years, 10 died in 4 years, 15 died in 6 years, and so on. But by the end of 11 years, we only had 90 deaths. We do not know the status of other 10 patients. The 10 patients were present during the start of the study, but left prior to their death or left somewhere between the 11 years. We cannot report this as their death, or we cannot simply ignore this data. This data in a statistical term is called censored data. In the next slides, we will see the statistical method we can use to create survival function for this type of data. Well, previously we had assumed that we know the probability of patients dying at specific years for calculating our survival function. The reality is we don't always have this information with us. In such cases, we rely on a statistical method to estimate the survival function. Some of the commonly used methods are Kaplan-Meier estimator, Nelson estimator, and Cox proportional hazard model. We're only going to discuss the Kaplan-Meier estimator today. The Kaplan-Meier estimator, also called the product limit estimator, is particularly useful when dealing with censored data. It uses the time to event data directly and helps us create a stepwise survival function. Okay, we will start with an example of our cancer patient. Let's say we are interested in the mortality of 50 cancer patients. For simplicity, we are going to assume that they all got diagnosed with cancer at the same time at the study of the period. We are going to record every time a patient dies or when we lose their data. If we look at the first row of 10 patients, we can see that there was 3 deaths recorded in month 4 and 2 deaths were recorded in 5-month period, 2 in 6 months, and so on. The next row we can see that another death was recorded in 8 months. And now we have a censorship situation. The 8 asterisk means that we do not know the condition of this patient from month 8. This patient was alive for the first 7 months, but we are not sure what happened to them after this point. So we cannot just ignore this data from the beginning. The next 4 dates were recorded in month 9, and again we lost some data in month 9. And another 2 more dates were recorded in month 10, and so on. And the last 4 data were censored at month 24, which can either mean that we are not able to get their data or we stop our study after this time. You can see that we have recorded 3 deaths in time 4, 2 deaths in time 5, 2 in time 6, and so on in the death J column. For the censored data, we have recorded them all in the appropriate row. For example, 1 was censored in time 8, 2 were censored in time 9, and so on. And now risk J is one of the most important column here. It represents the number of patients that are in the study that are currently at risk. For example, in the beginning there were 50 patients at risk, and after 3 deaths in time 2, 47 patients were at risk, and so on. And for time 9, even though there was only one death occur in time 8, there was a censored data. So in time 9, there are now 38 lives at risk. Because we lost this data, we cannot count this person in our risk spectrum anymore. Similarly, in time 8, 4 deaths were recorded and 2 were censored. So we have 38 minus 6 equals to 32 lives at risk. Now we are ready to use this table to create our survival model. So how can we use the Kaplan-Meier estimator, also known as the product limit estimator, to find the survival function? The KME calculates the probability of survival at each observed time point by considering the proportion of individuals still alive at that time. Mathematically, the estimator works by multiplying together the conditional probabilities of survival at each observed point, which looks like this. And using this formula, we can create the survival probability of individuals at each time. We started our observation with 50 cancer patients, and from the table we can see that 3 deaths were recorded in time 4. Hence we know the probability at time 4 is 3 over 50, which clearly means that the probability that a patient dies in the 4th month is 0.06. But we are more interested in the survival of the patient after 4 months, which is what the survival function is all about. Hence, the probability that a patient survives more than 4 months or doesn't die in the first 4 months is 1 minus 0.06, which is 0.94. For J equals 2, which is time 5, the probability of death in the 5th month is 2 over 47, which is 0.0426. As 2 deaths had occurred in the 5th time out of the 47 patients alive. Now, the question is, what is the probability that a patient will survive more than 5 months? To survive more than 5 months means that a patient has to first live for first 4 months and then not die in the 5th month, which means that our S hat 5 will be the product of the probability of patient surviving more than 4 months, which we have already calculated as 0.94 in the previous part, and the probability of not dying in the 5th month, which is 1 minus 0.0426 or 0.9574. Hence, the probability that a cancer patient survives more than 5 months is 0.9. Similarly, we can use the same conditional probability and product limit estimator idea to calculate the survival probability for time 6 and others. Consider the censored data while calculating other survival probability. We can notice that the survival rate has in fact decreased over time, which is what we expected from the beginning. Using the survival probability we have calculated, we can finally create our survival function. As we can see, it does not take any parametric shape, but solely relies on the data we have passed. We can read this as the probability of a cancer patient surviving more than 5 months is 0.9, and the probability of a cancer patient surviving more than 10 months is 0.65. In summary, Using data, event time, and model alongside with the Kaplan-Meier estimator, survival analysis provides us a framework for understanding real-life time-to-event data and helps us derive actionable insight to make strategic and risk-effective decisions. Thank you for watching.